A statistical model embodies a set of assumptions concerning the generation of the observed data, and similar data from a larger population. A model represents, often in considerably idealized form, the data-generating process. The model assumptions describe a set of probability distributions, some of which are assumed to adequately approximate the distribution from which a particular dataset is sampled. A model is usually specified by mathematical equations that relate one or more random variables and possibly other non-random variables. As such, a model is a formal representation of a theory. All statistical hypothesis tests and all statistical estimators have derived from statistical models. More generally, statistical models are part of the foundation of statistical inference. Formal definition. In mathematical terms, a statistical model is usually thought of as a pair which contains a distribution that adequately approximates the true distribution. Note that we do not require that contains the true distribution, and in practice that is rarely the case. Indeed, as Burnham and Anderson state, a model is a simplification or approximation of reality and hence will not reflect all of reality, whence the saying, all models are wrong. The set is almost always parameterized. The set defines the parameters of the model. A parameterization is generally required to have distinct parameter values give rise to distinct distributions, i.e., to meet this condition, a parameterization that meets the condition is said to be identifiable. An example: height and age are each probabilistically distributed over humans. They are stochastically related. When we know that a person is of age 10, this influences the chance of the person being 6 feet tall. We could formalize that relationship in a linear regression model with the following form: height equals b0 plus b1 ag plus epsilon I, where b0 is the intercept, b1 is a parameter that age is multiplied by to get a prediction of height, epsilon is the error term, and I identifies the person. This implies that height is predicted by age, with some error. An admissible model must be consistent with all the data points. Thus, the straight line is not a model of the data. The line cannot be a model, unless it exactly fits all the data points, i.e., all the data points lie perfectly on a straight line. The error term, epsilon I, must be included in the model, so that the model is consistent with all the data points. To do statistical inference, we would first need to assume some probability distributions for the epsilon I. For instance, we might assume that the epsilon I distributions are I.D. Gaussian, with zero mean. In this instance, the model would have three parameters: b0, b1, and the variance of the Gaussian distribution. We can formally specify the model in the form: each possible value of equals determines a distribution on, denote that distribution by, if is the set of all possible values of then. In this example, the model is determined by specifying and making some assumptions relevant to. There are two assumptions: that height can be approximated by a linear function of age, that errors in the approximation are distributed as I.D. Gaussian. The assumptions are sufficient to specify, as they are required to do. General remarks. A statistical model is a special type of mathematical model. What distinguishes a statistical model from other mathematical models is that a statistical model is non-deterministic. Thus, in a statistical model specified via mathematical equations, some of the variables do not have specific values, but instead have probability distributions, i.e., some of the variables are stochastic. In the example above, epsilon is a stochastic variable. Without that variable, the model would be deterministic. Statistical models are often used even when the physical process being modeled is deterministic. For instance, coin tossing is, in principle, a deterministic process, yet it is commonly modeled as stochastic. There are three purposes for a statistical model, according to Konishi and Kitagawa: predictions, extraction of information, description of stochastic structures. dimension of a model. Suppose that we have a statistical model. Here, D is called the dimension of the model. As an example, if we assume that data arise from a univariate Gaussian distribution, then we are assuming that, in this example, the dimension D equals 2. As another example, suppose that the data consists of points that we assume are distributed according to a straight line with a, I, D, Gaussian residuals. Then the dimension of the statistical model is 3. The intercept of the line, the slope of the line, and the variance of the distribution of the residuals. A statistical model is non-parametric if the parameter set is infinite-dimensional. A statistical model is semi-parametric if it has both finite-dimensional and infinite-dimensional parameters. Formally, if D is the dimension of an N is the number of samples both semi-parametric and non-parametric models have as. If as, then the model is semi-parametric, otherwise, the model is non-parametric. Parametric models are by far the most commonly used statistical models. Regarding semi-parametric and non-parametric models, Sir David Cox has said, these typically involve fewer assumptions of structure and distributional form but usually contain strong assumptions about independencies. Nested models. Two statistical models are nested if the first model can be transformed into the second model by imposing constraints on the parameters of the first model. For example, the set of all Gaussian distributions has, nested within it, the set of zero-mean Gaussian distributions. We constrain the mean in the set of all Gaussian distributions to get the zero-mean distributions. In that example, the first model has a higher dimension than the second model. Such is usually, but not always, the case. As a different example, the set of positive mean Gaussian distributions, which has dimension 2, is nested within the set of all Gaussian distributions. Comparing models. It is assumed that there is a true probability distribution that generates the observed data. The main goal of model selection is to make statements about which elements are most likely to adequately approximate the true distribution. Models can be compared to each other. This can either be done when we have done an exploratory data analysis or a confirmatory data analysis. In an exploratory analysis, we formulate all models we can think of, and see which describes our data best. In a confirmatory analysis we check which of the models that we have described before the data was collected best fits the data, or test if our only model fits the data. Common criteria for comparing models include R2, Bayes factor, and the likelihood ratio test together with its generalization relative likelihood. Konishi and Kitagawa state, the majority of the problems in statistical inference can be considered to be problems related to statistical modeling. They are typically formulated as comparisons of several statistical models. Relatedly, Sir David Cox has said, how the translation from subject matter problem to statistical model is done is often the most critical part of an analysis.